Okay, so good afternoon, everybody. So this is my last Gresham lecture of this academic year, and I'm going to take you on a slight trip towards the future and discuss what I call existential risk. And I really mean risk to the Earth, actually, and I'll be covering quite a few issues here. So what do I mean by existential risk? So this was nicely defined by an Oxford philosopher who defines it as follows. Existential risk is where an outcome would either annihilate Earth-originating intelligent life or permanently and drastically curtail its potential. So this is bad, right? The risks that we may be facing. Much worse than we can imagine for Brexit, etc. Okay, so this is long term. Okay, so let me begin with some examples. And I'll be discussing these in a little more detail, but let me just show you the sorts of risk that are pretty serious here. So an asteroid hitting the Earth. We're well aware that about 60 million years ago, there was a massive impact which destroyed who knows how many types of species, including the dinosaurs, and did incidentally probably clear the way for Homo sapiens. A nuclear holocaust. There were worries from the first testing, even before, the notion of chain reactions in nuclear physics, that these could just ignite a potential nuclear holocaust and destroy the Earth. The scientists worried about these things, that I will explain in a moment. Nanotechnology, sometimes referred to as the revenge of the grey goo. These are maybe misuse of nanobots, which could, destroy our entire biosphere and not leave much behind for us to survive. And of course, at the same time, this is a technology that's critical for much of our current way of life, actually, for commercial developments, etc. Artificial intelligence is another issue that I'll describe. Now, this is something that does depend on the computer programmer. And you can imagine that if these things are badly programmed, there could be, again, some future disaster arising. We haven't quite got there yet with misuse of Google, but that's the sort of thing that could happen in a much more dramatic way as our computers become much more powerful in the future. Genetic engineering, another example of the amazing power that we have now in biotechnology. And this could go in a bad way too, maybe by accident, maybe through terrorist activity, whatever. I'll give you some examples. Here is maybe one of the most bizarre possibilities. If you think ahead to the future, we will have such powerful computers that the children, in who knows millions of years, will be playing their video games and simulating the past. And we might actually be in a computer simulation without knowing it. And that could be shut down. Someone could turn it off, and that would be a catastrophic end. And then, all these are examples that people worry about. The last one, mostly philosophers rather than scientists, but that's. And then something that we haven't even dreamt of yet, something unforeseen, could be a source of existential risk and total or dramatic destruction. So let me begin with worries about the impact of a meteorite. And Stephen Hawking was very concerned about this. He wrote, although the chance of a disaster to planet Earth in a given year may be quite low, it adds up over time and becomes a near certainty in the next 1,000 or 10,000 years. Okay, so I think he was a little pessimistic on that, but I'll tell you what I think the odds are. So let's consider this. Here are examples of meteorite impacts. Maybe one of the most elegant ones, some of you may have visited, is in Arizona. Just 50,000 years ago, this is 1 kilometer across, Meteor Crater. Here is one from 1 million years ago or so in Canada, larger one. You know, the further back in time, the likelihood of a bigger event is more likely, etc. And this is one of the bits of meteorite found in this crater. Here is one dated to have been a couple of billion years ago in South Africa, the Vredefort Dome. And this is several hundred kilometers across. Most of it's hard to see, but this is a satellite photograph. And so in an enormous area, impact of an asteroid, probably not that enormous actually, maybe less than a kilometer across, we imagine. And so these impacts would release enormous clouds of dust. And with a big enough impact, we might expect something as bad as this. And this is roughly a visualization of what might have happened about 60 million years ago when there was an impact, most likely, that led to a huge cloud of smoke that covered most of the Earth. Sunlight was dramatically reduced, and this is thought to be one of the major reasons that there were mass extinctions, including that of the dinosaurs. This is just an artist's vision of how dramatic this might be. So let's just think about what the odds are for this sort of thing to happen. Well, here is another worry that we have. How do you want to figure out where these asteroids might be, what the chances of finding one before it will hit the Earth, and maybe diverting it. I mean, so there are clever ways you can imagine to divert them. One is if you find one, you could launch a missile at it and try. All you've got to do if you find it far enough away is divert its course a little bit, and it will miss the Earth. But what's amazing is we're beginning to track debris that goes around the Earth. And so this is, you can see here the orbit of the Earth and beyond Mars. And these are all orbits of debris that are being tracked. Now, these are human-initiated debris. They come from old satellites that have begun to break up for whatever reason, collisions with other satellites. And there are many thousands of bits of metal and plastic in orbit, maybe up to 10 centimeters. There might be nearly 1 million of these things, and smaller ones, many millions. We don't know, we can't see them. We just speculate. Because, you know, when things grind together in a collision, they will make many smaller things too. And these are potentially very dangerous things, because if you want to launch a spacecraft from the Earth to anywhere with humans inside, then the chances of running into one of these are non-trivial, and even something a few centimeters across, which will hit you at many thousands of miles an hour, could be very dangerous indeed for spacecraft. So that's why the space agencies track these things and try to limit a safe path. So the same instruments that do this tracking would also be able to look for asteroids far away. They would look much like one of these nearby bits of debris, and this is a proposed small telescope that will looking for what are called NEOs, near-Earth objects. So it's a smallish telescope, but with a huge field of view. And the idea is that it would be launched and just scan the sky again and again and again, looking for things that move slightly. And this then would be an indication that something is coming towards us. If you catch it far enough away, it could be a significant asteroid that might potentially harm the Earth. So we haven't launched this thing yet. Other devices are looking for them too. We've had 1 or 2 false alarms of asteroids which have come and had near misses with the Earth, but so far nothing much. And that's because these things are very unlikely. But we've only been looking for the past decade or two, so who knows what might happen in the next 1,000 years or the next 1,000,000 years. Okay, so let me try to give you a feeling for how likely this is that there could be a huge risk from a major impact, as happened some 60 million years ago, when we have actually traced off the coast of Mexico, off the Yucatan, the area now under sea where there was this major asteroid impact, which then led to a huge cloud of smoke and pollution, which cut off the sunlight, warmed up the Earth, etc., and did lead to major extinctions. Okay, so suppose indeed we accept this. It's our best theory so far, 60 million years ago. And imagine this were to happen again, and the worst possible conclusion is that one might lose a few billion people, right? Because of this, the many terrestrial fires or whatever, explosions ignited by this huge impact around the globe, perhaps, okay? Maybe it would trigger volcanoes all over the place. No one really knows what the consequence might be. But this is the most risky thing you could imagine happening. So let's suppose you lose 6 billion people on the average every 60 million years. That's a worst case scenario. Well, that's roughly, if I've done my arithmetic right, about 100 per year. Okay, so on the average then, it's no worse than the probability of anyone dying in a plane crash, okay, commercial plane crash. So, and probably the chances of dying in a road accident, of order are probably even much greater than that. Okay, crossing the road or whatever, or being hit by, a driverless car or whatever our future dangers might be. Okay, right. So, so we shouldn't be too worried. But the Earth, is billions of years old, so we can have a record of this. But our civilization is only really, in terms of post-industrial revolution, a couple of centuries old, and we have many thousands, many millions, even billions of years to go if we can keep our act together. And so bad things could happen in the future over a long enough timescale. One has to think about these things. Okay, so now, asteroids aside, let me turn to another worry that people are having. And so this is to do with artificial intelligence, which, as you know, is a major component of Facebook, for example, and all of our major internet activities developing very rapidly. And computers are just becoming more and more powerful. We can do more and more with this. And again, let me quote Stephen Hawking: the development of full artificial intelligence could spell the end of the human race. And I'll try to explain what he meant by that. So this is, and this is the idea that, as computers become more and more powerful in the future, either by bad programming or possibly there could be some random error that could lead to computers developing with malicious intent, right? And this is a worry for artificial intelligence. So how far have we gotten? Well, right now, the most complex game that we probably have is Go. And Google's artificial intelligence has just, on a computer, has just beaten the world's best Go player. And so there are more moves in Go, as I write, than atoms in the universe. It's truly a complicated game. And as you know, the idea is to surround your enemy, black surrounding white, etc. And so, well, we've already lost the best chess players to the artificial intelligence. Now it's Go. So what about the future? Well, again, the computer age is just not very advanced, right, compared to what it will be in the future. We have some potential robot here who is not only vastly more physically powerful, but vastly more intelligent than our human. And let's hope that, it's happy to play games and be friendly. Okay. Okay, so how old is the computer age? Well, these are the two pioneers of the modern computer age. Ada Lovelace was the daughter of Byron, who did the first programming for computers, and Charles Babbage, a Cambridge mathematician, who built the first computing devices, analog computers. And between them, so they launched in the 19th century the modern computers, okay? And now computers are becoming more powerful. So what is the what is the future for computing? Well, what you have to think about now is what I just showed you was from 2 centuries, over 2 centuries, okay? That's our history. But the Earth is about 4.6 billion years old. And there are other stars out there, and that's the age of the sun as well, right? Everything happened at that time. And that's when the solar system began, okay? Now, there are other stars which are billions of years older than our sun. We know that. We can date them by taking their spectra, by examining their light. And we also know that planets like the Earth are truly numerous. We call them exoplanets, and we've begun to find thousands of them around nearby stars. And for these exoplanets, we have no idea if life is on them or not. It's very, very hard to even look at the moment with technology for life tracers, such as oxygen in the atmosphere and other activities. Pollution in the atmosphere, that'd be a great thing to look for, right? Industrial pollution, things like that. So we haven't even got to that point yet, but those are future activities we'll be thinking of, and maybe even imaging these things eventually with big enough telescopes. But that's all for the future. But what is clear already is that while we have no idea what the chances of life might be, many of these exoplanets, twins of the Earth, if you like, have a huge head start on the Earth. They would have been formed and having the same conditions as the early Earth had, but, you know, 1 billion years ahead of us. And if life were maybe some random occurrences, you know, there are, who knows, there are billions of stars in the universe that we can infer from our biggest telescopes, actually billions of stars. And so even if a few of these had life on their exoplanets, that life could be so far advanced that it might have, we can't begin to imagine how powerful that might be. And so we just don't know. The potential is totally unknown. So now we hope that this life elsewhere, if indeed it exists, it seems likely it should somewhere, that it basically is benign. It doesn't have any strong, you know, ambitions against destroying more primitive forms of life, as did happen in our recent history on the Earth. I'll come to that in a second. But, you know, who knows? So one has to keep an open mind on this. I hope it's more positive than negative. There are scientists among my colleagues who say you should not be trying to communicate. There's a whole program called Search for Terrestrial Intelligence, which tries to send out radio signals and listen to radio signals coming from planets that are not too far away. You remember, we've been broadcasting radio signals since, you know, radio, if you like, TV shows like Lucy or whatever, since the 1940s. And these shows move out at the speed of light from us. And so if you have planets that are within 100 light years of us, they'd be receiving our early TV transmissions from a century ago. Who knows what opinion that would give them about the Earth, right? But anyway, whatever, that's what they'd be seeing. And so we can't avoid that. And there are, you know, and then one can imagine trying to send signals or listen into them. And some scientists say, well, it's dangerous to draw too much attention to yourself because who knows what what could come of that. Unpredictable. There's a debate that goes on. And so why do I think that the rise of future computing is so is unlimited, basically, compared to what we have these amazingly intelligent artificial intelligence systems now, but in the future it's hard to believe. So this shows you the rise of computing power since the early days, and it just doubles by a factor of 2 every year or so, basically, and that means exponential growth. So you can see these are in the early analog computers, right? This was Babbage's analytical engine. And now we've increased by, and so by factors, this is a minus sign in front of that digit, here's a plus sign. So we've gone up by many, many orders of magnitude, okay? And so it's what we call exponential growth. And so here we are basically where we'll be very soon. IBM, now the world's most powerful computers in China. This is it. Just begun operating, or about to operate this year. It has, it has a power of what we call 1 exaflop. It's more powerful than any American computer or European computer by a significant factor. although other countries are rushing to catch up, of course, and they can do this enormous number of operations every second. And so that's where we are. But there's no obvious limit to this, because we may well have be coming towards near the end of what we can build in terms of simple chips, silicon chips, but there are whole new technologies coming in which rely on, you have numbers of 0 and 1 which you use to program computers and devise programs. But in principle, if you can go to what is quantum computing, you can go to a whole new area where these numbers are virtual, they're unlimited in the number of combinations you can have, and so one can, as we're beginning to develop or study this technology, we're far from mastering it now, but it seems clear that in the next decade or whatever, we should be there with future growth totally unclear what would ever limit it. Okay, and so this is the view of a pessimist. This is an interesting book to read, who says that artificial intelligence will go beyond the capacity of the human brain. Now, it's already there beyond the ability to play Go, but this is now something a little more advanced than just playing games. It will have consciousness or whatever, and that will be within a decade or so. And at that point, we would have to start worrying about whether humanity would be replaced, it would be natural evolution for it possibly to be replaced by computers. So there'll be a significant change in our computing ability when computers overpass the human brain in an order of decade. So Kurzweil claims. Okay. So what about consciousness? Well, we often think that the one thing a computer cannot be is conscious, right? A computer cannot write poetry, can't write Shakespeare or whatever. I mean, it doesn't quite have it can't fall in love with another computer, but are we so sure of that, right? So I think the answer is we're in unknown territory here. So as you increase, the power of simulating things in computers, you start some very crude representations of humans, and then you get more and more sophisticated. And then at the end, maybe you have something that really is indistinguishable from a human. We have no idea. There's just a certain number of synapses, billions that go on in our brains. And when you can overcome that with computers, then, those random combinations may a human being as it might be indistinguishable. Okay. So, and then you worry about whether, again, because of bad programming or something, or just a random errors creeping in, there could be some malicious intent that might evolve. That's what Kurzweil worries about in those computers. Kurzweil worries about, and that would then lead to a disaster, an exponential risk to humanity. And we've, seen the glimmerings of the possible risks already with the misuse of artificial intelligence in applications, already on the internet. And so this is just presumably the tiniest taste of what is to come in the future, unless we begin to develop regulations that can, control this to a great extent than we have today. And I'm sure that will happen. Okay, so here now, let me move on to threats, existential threats that won't necessarily be completely fatal for humanity, but would, have a pretty big impact anyway. And so you can think of these as quasi-existential threats because, if they destroy some large fraction of the people on the Earth, we'd survive, pretty robust species, but these are bad things that we don't want to happen. So let me just mention some of those. One of them is just the use of nuclear weapons, of course, nuclear war. Some newspapers are now telling us to start worrying about this again as the Cold War heats up again. But, who knows? We've been through this before. Maybe we'll all survive. There's degradation of the environment. It could be so bad that, it may be very difficult for our current way of life to survive. That might be many more deaths, etc. Disease, mass diseases. These are very hard to control. New things can arise, random genetic mutations, and they can cause major events that are threats to humanity. And just the whole global warming may make life on the Earth very difficult. We could become, in principle, if the greenhouse effect develops more because of pollution, trapping the heat. In the atmosphere, that could lead to our being more or less like living on the surface of Venus, which should not be a very pleasant place. Okay, so we've known about these dangers for quite a while. So it's interesting to look at what we historically, to look at what happened around the time of World War II when the first atom bombs are being tested and used. What were the scientists thinking? Well, the scientists who developed the atom bombs dropped on Japan tried to envision the kind of nuclear event that could lead to destruction of not just cities, but the entire world. This was in the 1940s, they worried about this. The verdict that scientists at the Los Alamos lab and test site reached in 1945 found that it would require only the neighborhood of 10 to 100 super bombs to put the human race in peril. Now, what they meant by a super bomb was what later became to be called the hydrogen bomb, something roughly 1,000 times more powerful than the bombs dropped at Hiroshima and Nagasaki. Okay. 10 to 100. Well, we didn't listen to that too carefully, and there have been a number of nuclear tests, atmospheric tests carried out. Unfortunately, not too many. So here are the two record holders for nuclear tests in terms of megaton power. Remember, the Hiroshima event was awarded 20,000 tons, 20 kilotons. These are thousands of times more powerful, these hydrogen bombs. This was on the Bikini Atoll, a US attempt, and then the Russians outdid the US with what they called the Tsar H-bomb, which had 60 megatons, and that was in 1961. Okay, so we've learned our lesson from that, and that all led, within a couple of years, to an international treaty banning atmospheric testing. And so it's interesting to look around now and look at the landscape. So the interesting thing is that not only are there areas of the world devastated by nuclear testing, but interesting enough, it's also just burning coal that leads to acid rain that destroys enormous areas, that has almost as devastating an effect on our environment. So here are a couple of quotations. In the Adirondacks in northern New York State, the acid rain includes a mixture of sulfuric and nitric acids from the sulfur dioxide and nitrogen oxides pouring from the smokestacks of power plants, smelters, factories, and vehicle exhausts. Over 200 lakes are dead, their aquatic life gone or dwindling. And it's not just the US. In Scandinavia, acid rain has destroyed 15,000 lakes in recent years. Inevitably, the death of a lake affects other wildlife as well. Fish-eating ducks, loons, otter, mink, and even birds begin to leave because their food and shelter have been destroyed on the ground. Acid rain leaches essential nutrients from the soil, calcium, magnesium, potassium, and sodium. It prevents seeds from germinating, scars leaves. Okay, and then, turning to Russia, and this was in the vicinity where they were doing nuclear testing and nuclear experiments. About another eyewitness account, about 1,000 kilometers from Sverdlovsk, a highway sign warned drivers not to stop for the next 20 or 30 kilometers to drive through at maximum speed. On both sides of the road, as far as one could see, the land was dead. No villages, no towns, only the chimneys of destroyed houses, no cultivated fields or pastures, no herds, no people, nothing. What I saw personally was a large area in the vicinity of Sverdlovsk, no less than 100 to 150 square kilometers, and probably much more, in which any normal human activity was forbidden, people evacuated and villages razed, evidently to prevent inhabitants from returning. There was no agriculture or livestock raising, fishing and hunting were forbidden. So, fortunately, these areas are still limited, but, one has to worry. So now let me go from nuclear and environmental concerns to issues of diseases, mass diseases. And so again, there's been an interesting history of this over the past couple of thousand years, even a few hundred years. You can see how the plague, the Black Death in London, and indeed throughout Europe actually at different times, had catastrophic effects on the population, right? So this happened in the 14th century, the population going down dramatically by 25%. And then in the 16th century there was another episode, not quite as dramatic, but many millions of deaths. So these are things that one would love to try to understand better. And given that these have happened within the past, couple of hundred years, who is to say what might happen on a timescale that's much, much longer as new mutations of diseases develop? Here's another example of how just indigenous people not in contact with more developed areas where there was more immunity to disease were affected. This is the indigenous peoples in Southern America, in Mexico in this example. And so you can see just smallpox alone led to enormous population decreases. In fact, many millions of deaths, and these were substantial numbers of the fractions of the population, right? Just going down, sort of 90% or as much as 90% being affected of the indigenous population. So these are risks for the future. These things could occur again. We have to think about how to control them. And so the worry about their occurring again is that we're beginning to understand how to make these genes more. I'll come to that again in a second, and want us to worry a bit about genetic technology leading, not inadvertently leading to escape of viruses, whatever that could be bad. Okay, what about another environmental problem, that is sea rise, okay, from global warming. So you can see in the South Antarctic region, a huge ice continent that's gradually melting away, okay? And so this is the melting of the ice, and that is such a huge area that is already beginning to melt. This will lead to significant rise of sea. And so these are projections, and so you can see the worst case and the optimistic case. And so let me just, and this is in centimeters, so we're talking about 12 possible, a 12 meter rise in sea level over, it's cut off here, this is over 200 years, okay? And that's huge. So if you have a 12-meter rise, London will be mostly flooded. Okay, we'll have a few skyscrapers to live in, of course, but that may be good. But so one has to, and if you're optimistic, then instead of tens of meters, it's 5 meters still. But still, that's a lot as well. So, okay, right, and if. So some people argue again, Stephen Hawking again, we're close to the tipping point where global warming becomes irreversible, to become like Venus with a temperature of 250 degrees and raining sulfuric acid. So this is an example just of on the Earth, actually, of what typical areas might be like, baked by the sun. And of course, what's happening is that pollution, basically, in the atmosphere is stopping the sunlight, which turns infrared light heat on the ground from leaving, and things just heat up as in a greenhouse. So that's the worry, and we may be getting closer to a rapid increase. That once this begins, there could be a runaway effect. That's what Hawking worries about. Okay, and then let's go back to diseases and things. And so, I showed you the natural cases of outbreaks, which we have to somehow learn how to control in the future. Well, I'm sure we will as our technology gets better, but already there are issues that are worrying some people. And so one can lump this under the name of genetic terrorism. So the idea is that one can now begin to synthesize in the laboratory some very nasty viruses. Okay, and so these are now published in the open literature. And so this particular article worries about whether research is crossing a red line in the field of biosecurity. It's put out by a US agency. But, it's a sort of indication that one has to be a little bit careful, because if technology falls into the wrong hands, then it could lead to, again, major outbreaks that will be very hard to control. Okay, or there's the other possibility of having an accident, right? So in these high security labs that are designing these things and controlling them and seeking remedies against them, that's very important to do. There could be accidents, and that could lead to escape of viruses. So one has to, these things, will almost never happen. But the future's a long time, and even though the risks are incredibly small today, you want us to worry about what could happen in the future and control these things. So basically, the problem in all this is that the Earth is a very, very fragile place, right? And as Carl Sagan said, our posturings, our imagined self-importance, the delusion that we have of some privileged position in the universe are challenged by this point of pale light. So that's the Earth as seen from Apollo, and this is the pale blue dot as seen from 6 billion kilometers away by the Voyager spacecraft. That's all we are. And if you get further away, you'll see nothing at all, of course. So that's the Earth as seen from far away. Okay. Let me now turn to physics, okay? I'm a physicist, and I want to describe to you a danger that physicists have been accused of raising, okay? So they've built this machine, 27 kilometers in circumference, a tunnel under the ground where you have beams of high-energy particles being sort of a magnets in opposite directions. They collide with each other at vast energies. And the idea is to study new physics. Okay, so that's been around. That was built a decade or so ago. And there was a worry, and this is an example of one of the collisions inside this, one of the big detectors. And so in this collision of particles, they produce debris. And there was a theory in existence before they built the collider that said, well, maybe it's possible I could make tiny black holes in these very energetic collisions. And this is one of the theories still popular at that time, still popular, in which you envisage that we live not just in a three-dimensional world, but there are higher dimensions too, but right now they've all just compressed down to something very tiny, unmeasurable, and in those tiny dimensions there would be black holes. But at very high energy, you can break these things open. So suddenly, out of almost nothing but fed by high energy, you can make tiny black holes. And so this was taken seriously enough. So there was a law case against this doomsday accident. If you made a black hole, that could be really catastrophic in principle in your laboratory. And it went to court, and it was dismissed by the judge. And then they allowed the Large Hadron Collider to be built. And they, the people who filed the lawsuit worried that this might threaten the Earth. Well, we believe that's not true. And so this is why. It's certainly true that you can make these tiny black holes. But if you go through the energetics of how big these black holes are, they're roughly constrained by the energy you put into your beams of particles. And that means a mass which is really, really tiny. So in grams, it's much, much less than a trillionth of a gram. Okay, and so fortunately, these evaporate. So again, this was one of Stephen Hawking's major contributions to physics. He predicted that what can happen is that these things we call the mini black holes would just disappear. They just couldn't, they were just so small that they would be intrinsically so hot, basically, because their surface is so curved. Curvature means power of gravity in Einstein's language, that they would just radiate particles like crazy. And the way it works, we call this Hawking radiation, is that the particles, split up in space into pairs. One particle out of nothing, they're vacuum. It happens in the vacuum, we call them fluctuations. Some fall in, some come out, and the ones that come out, if they go to infinity, that's evaporation. So basically that's how they work, and Hawking showed this happened so quickly that this couldn't possibly be a danger to humanity. So of course that was a theoretical expectation, but theory is never quite enough to convince a judge in a lawsuit, and so there were two other arguments which were equally important in the lawsuit, I think. And one was that we've been bombarded on the Earth by cosmic rays from space throughout the existence of the Earth, and these cosmic ray particles, some of them are at much, much higher energies coming in than ever we could get to in the Large Hadron Collider. And so these particles then coming from outer space, from distant explosions, distant galaxies, hit the Earth, hit the atmosphere and collide, and lo and behold, as far as we know, no one has ever seen a mini black hole being produced. So that's another example. Then the final argument, which is that, again, in physics, we have to demonstrate what the risk might be. Risk assessment is what the lawsuit was about. And so the risk assessment was that we can calculate that if they ever did succeed in getting past these other two barriers and making a tiny, tiny black hole in this collider, then true, it would not swallow up the Earth. It would just accrete so slowly, just by physics, that it couldn't possibly be a risk. And it might fall out the outside of the Earth and go off wherever, because it's so dense, but it just would not be a risk to the Earth. So all of those arguments meant that, fine, we could go ahead and do these experiments on the Earth. Okay, so now let's talk about another way to avoid this risk issue, okay, escape. Let's imagine that we go to Mars, build a colony on Mars or the Moon, okay? And so here is one of the problems with this. Space is full of debris, okay? And so here are examples of the debris surrounding the Earth, just bits of old rockets and things, okay? And this is another simulation of all the debris that's being tracked. Many thousands of bits of metal moving at 18,000 miles an hour relative to a spacecraft going through them. This is pretty dangerous. You have to somehow, pilot very carefully to avoid collisions with this debris. So that's sort of one has to get over these dangers. Then there are other issues if you want to go to Mars. Here is another one. It turns out that we are just beginning to understand the medical risks of a long voyage in space. So this applied not to people spending 1 year on a spacecraft to Mars, 9 months, whatever it takes, but just going around the Earth on the International Space Station, not very far away, in very low gravity. And they were found, finally we've done detailed medical studies of them. It takes time to follow them, the astronauts, that is. And from the Apollo days, and they're 5 times more likely to die from heart disease. And this is from relatively, nearby ventures in space. And we have no idea really what the risks might be in getting after a long journey to Mars. Whether, in fact, when you got to Mars, a human will be in any state to basically survive for very long. We have no idea. All of that's a study of, so maybe going to the Moon is a better way to escape, okay? It's closer. It's a much shorter journey to the Moon. It's instead of, whatever, hundreds of millions of miles to Mars, it's just 250,000 miles to the Moon. So it's a short journey. And so the Moon is actually a very interesting place that's being discussed now as a future base. And again, if things go bad on the Earth, you want bases somewhere else, and you could then go on elsewhere from the Moon maybe. So on the Moon, the good news is this. There are deep craters on the Moon, lots of ice in apparently. So ice is great because with ice you can break it up, you can get hydrogen for rocket fuel, you've got water, oxygen to breathe, you've got water to fabricate bricks and things. Again, with moon dust, you can do construction on the Moon. It turns out that some of these craters on the Moon, very dark in the inside, full of water and ice, have high rims, always in the sun. I'll show you a picture in a second. So great for solar power. You also have helium-3, a rare isotope of helium, which is doesn't exist naturally on the Earth, but it's abundant on the Moon because the Moon's been bombarded with cosmic rays from the sun for billions of years, and it's made by cosmic ray impacts on the surface of the Moon. And that's great for clean nuclear fuel, thermonuclear fuel. It's thought to be one of the major things we need, and then that would help a lot. Lots of rare elements from the bombardment of the Moon over the years, huge commercial advantages to go there. And finally, you could even, with the water, do farming on the Moon, hydroponic farms. You don't need Earth, actually, just some atmosphere and water, basically. And so all these things are being studied to go to the Moon. And so when we get there, this is what we might find. So first of all, a good place to go would be to one of the 2 poles of the Moon, because that's where the climate is not too extreme, because it's like being almost in a permanent twilight zone. So near the South Pole, there are some huge craters that are perpetually dark. They're always in shade, and they're thought to be full of ice, and they're surrounded by these high rims. And then near the North Pole, it's interesting, there are fewer craters, but what they found are these boreholes, which are thought to lead to much larger cavities inside, underneath, basically excavated by lava flows, past lava flows. So first of all, here's a close-up of the Shackleton crater. And so this is 4 kilometers deep, the enormous rims, 21 kilometers wide. It's been called the place of eternal darkness. It's always in shadow. But around it are these rims where there's sunlight throughout the year. So you could put up solar towers here, get lots of power that you need and build things away from the extremes of the extreme heat and the extreme cold, even build telescopes. And then on the North Pole, you can... It's thought, conjecture, it's likely, is that there'll be enormous possibilities for using lava tubes. So I'll show that in a second. So this is what ESA, the European Space Agency, is planning for about 2040. They want to have a base on the moon, this is obviously an artist's drawing, but they will do local construction, and they will have hotels on the moon and have business activities on the moon. They might even do some astronomy, that's to be seen. And then the lava tubes, and that's near the South Pole, it's a good place to go. And then here is what could happen in these lava tubes. So we think that these are just like skylights, okay? And that inside there's a huge area, and you can't quite see the bottom of this, but you could the entire, the city of London would basically fit about this area of this. And so these are thought to be, very high. This is the scale of 1,000 meters. So these are many kilometers across. And this is the sort of thing that you could build inside inside one of these lava tubes. You could build basically the equivalent of cities into these lava tubes. And you'll be covered from dust or other events coming from the sky, whatever. It'll be easy, presumably, to do construction there. One thing. So all to be explored in the future, in the next decades, but that might be another good place to go. Okay, so finally, another possibility, if you want to survive all this, is to try to become immortal. Okay, so this is, you might think this is crazy, but again, I have colleagues who take this very seriously. So, including one of my, Nick Bostrom, we mentioned at the beginning, a professor at Oxford. So basically, they have this. There's a society in Boston that offers to freeze you after death and preserve you for some transhuman future in who knows how many centuries, so you can be revived. And if you pay them, I think you can take out an insurance policy for this, roughly £100,000 a year or something, you can get your whole body preserved, and there's a cut rate if you want just your head preserved. And so that is what my Oxford colleagues, some of them went for. Okay, and this is where you'll be bits of you or your entire you will be placed in one of these, and hopefully the power won't be switched off, and so that's one way, another way to go maybe. Okay, so now let me go to the very far future. Okay, so the universe will get darker and darker if we can survive all these risks. Okay. Who knows? Okay, so maybe in 100 billion years we'll see no more stars, or very few stars, because all the galaxies will be accelerating from us. That's what we've learned from what we call dark energy in the universe. And the Milky Way, all the stars, like the sun, will have died out by then. We'll have things called white dwarfs, the remnants of things like the sun, neutron stars, black holes, maybe lots of planets. That's interesting. Okay, so this is the future of the universe. This is what we can see today. Roughly 15 billion light years or so. But as everything else moves away from us because it's accelerating, this is what we'll see in 140 billion years. Just our own galaxy, the Milky Way, that's it. Because we're being held together, we're not bits of that are not accelerating, but all the rest is moving away. So the night sky will look different in 140 billion years. But that's not fatal. But what else? Let's imagine there'll still be stars, there'll be dead stars, there'll be lots of planets, so life could go on. So the ultimate is that in a trillion years, our current theory says protons will decay. Okay, so that's bad news. And so we're looking for protons decaying. And so the idea, you can't possibly have an experiment which waits that long, but if you have enough protons in one place, in this enormous tank of water of order 50,000 tons of purified water, you can wait for the occasional random decay, okay? And that should occur. And so far, they've set a limit, a lower bound on the decay time of this, which is maybe a factor of 100 less than the absolute longest it could be according to our current standard of physics. So we're building bigger experiments to look for events like this to do better than that, okay? And a proton, this is the fate of a proton, so it will decay eventually into mesons and gamma rays, and that's what they look for in those experiments, mesons. But also it'll give you electrons, and electrons are particles that are forever. So we think so that they'll be left behind. Okay, so now let's imagine the really distant future. The protons have all gone, the electrons are left, so there is something in the universe. So can this allow any form of life to occur? Well, here is an interesting development in our thinking. So in the quantum theory, there are all sorts of random fluctuations. There's something called Heisenberg's principle, which is you could never pinpoint exactly, there's intrinsic uncertainty, you know exactly where a particle is. And so when you get to within the limits of that particle scale, things can come and go that you'd never see. And we call those quantum fluctuations. So things could pop out of nothing and go away for the tiniest fraction of a time, and you'd never know it, and that's consistent with the law of physics. In fact, it's even predicted by the laws of physics, because we believe there should be these generic fluctuations. So Boltzmann, who didn't know much at all about the quantum theory, was worried about the future of the universe and the rise of chaos in the universe. Entropy is what he called it. Chaos just keeps on increasing, and this would lead to what he called the heat death of the universe. In fact, he invented the second law of thermonuclear that predicts this, and it's worried him so much that he committed suicide, in fact. But anyway, quantum gravity is our modern solution to this. What this theory says is that there are fluctuations out there, and you know, they're pretty rare, but what is the most likely one? The most likely one is just basically our brains, our perception. And so these guys, and it's a general question in quantum gravity, problem actually, is that things that we now call Boltzmann brains would be the most, complete with all our memories, would arise spontaneously and disappear. And this is the most likely form of life when there's chaos everywhere, and basically nothing is left. Okay, so they just come and go. And so the universe, according to this picture of Boltzmann brains, endorsed strongly by some of my colleagues in the gravity community, would look like this. Here's a brain in the middle of space. It just comes and goes. And that, in some sense, would be what might await humanity in who knows how many millions of years' time. So my final thought for you is this, that can the universe live forever? Okay, so indeed, there are theories out there which say it could. So we call these the bouncing universe theories. And it goes back a long time, but they've become to be in fashion again because, you know, we don't really like the Big Bang beginning. It's sort of a singularity. It's not a good thing, nothing we really understand well. And so is there an alternative? So here's an alternative. The universe began from some infinitely large, almost infinitely large state, and it contracted and reached, you know, a finite but very small size, and then began to expand again. So instead of having the Big Bang to a very dense point, we have contraction to a finite point, then expansion, here we are, okay. And clumps form and make galaxies, all the usual stuff happens out here, and just the beginning was different. So this universe could have had no beginning, could have expanded from as large as you like, and in principle it could keep on doing this again and again, so it could also last forever. So that's the most maybe satisfying form of the universe. So, okay, so that's it for cosmology. Let me just end with one final point. Okay, so here's a quotation from Martin Rees. Spaceship Earth is hurtling through space, its passengers are anxious and fractious. The life support system is vulnerable to disruption and breakdowns, but there is too little planning, too little horizon scanning, too little awareness of long-term risks. And I'll end by showing you one of the immediate risks we can do something about. We are doing. This is space garbage. Okay, so this is all the stuff we have in space around the Earth. There are bits of stages of rockets and fragments of satellites that are broken up and all this stuff. And you can see over the years the numbers have been going up and up and up, and we have many thousands now. Okay, and so you might say that we should immediately try to clean up the garbage in space. That would be a great thing to do. And indeed, there are experiments launched of this. One was launched on Monday, a UK experiment actually, which is a trial sort of thing. It's going to have various nets and things to pick up garbage, and there are grappling projects in mind too, to pick up bits of old satellites and then bring them back to some safe place and get them out of the way. So, you know, cleaning up the garbage, cleaning up the rubbish in space is an immediate project that we might want to think about. But that'll keep us busy and maybe distract us from these very long-term risks I've talked about for the far future. So thank you.